Well, thank you for inviting me. This is a very interesting group. I've given presentations all over the country and actually all over the world, and this is a very good turnout for a local group. I'm quite impressed. Of course, MIT's name precedes itself, and I didn't graduate from there either. Okay, let me go. I'm going to introduce each of the three main threats, the high-altitude EMP from nuclear detonation, the intentional EMI, and geomagnetic storms, and very quickly roll into how these different types of electromagnetic fields can affect power systems, and then what do we have to do to protect. And that's, as mentioned, the standards are a key aspect of that, because we have to take highly technical information and translate it into something that can be built, constructed, and protected. I'll do a little bit of terminology. I'll go through the three main areas. I want you to note that the term severe geomagnetic storms. Most people don't realize, we have solar wind every day. There's a geomagnetic storm which I can measure in this room right now, but it's insignificant. It's not interesting. It's only the severe storms that we care about. And I'll finish up with protection issues. Okay, background. We know electromagnetic environment. People say, well, what's electromagnetic environment? Well, if you use a cell phone, you're using it every day. Over-the-air radio, AM, FM, satellites, mobile phones, Wi-Fi, these are all electromagnetic fields, except they're very low, typically on the order of a volt per meter. However, if you take your cell phone and the cell tower is far away and you lay it down on top of your computer, you may kill your computer because it's 100 volts per meter at a centimeter. And new standards are now being written for electronic equipment to survive that, because they often do not. Test levels, maximum test level is 10 volts per meter for an industrial PC. By the way, we're going to be talking about field levels of tens of thousands of volts per meter for the HEMP and the intentional EMI. Geomagnetic storms, much lower, but interestingly, they are also a threat. As we know, these are beneficial processes that we want to deal with. It really is important, though. A big change has occurred since we did our nuclear testing in 1962, our last high-altitude test, which I will talk about, is the fact that our electronics now operates in the gigahertz range, billions of cycles per second. That makes a difference. A lot of these environments not only are high, are also in that frequency range. So they have the ability to interfere much easier. That was not the case in the 1960s. And other high power threats we deal with: lightning, electrostatic discharge, and radar. Those are the main ones. Radar can create havoc if it gets close to commercial systems, and occasionally the Navy does get close by, and that can cause problems. But these are things that don't happen a lot. Lightning is the one that most people are aware of. It's at a much lower frequency range, and it only affects a limited area at a time. So I often refer to this as a triple threat. Some football fans like that. You have to go back to the early 1900s to know what the triple threat was. But the reason that they are being combined here is the protection techniques for all three of these have some things in common. And that's why we want to bring them together. Terminology: EMP. This was a term that only meant nuclear EMP 40 to 50 years ago. And in fact, the military designed its systems to survive, because in a nuclear exchange, electronic systems could be affected. And there were different types of EMP. The HEMP is a burst at high altitudes. Source region EMP is a burst on the ground. System-generated EMP is the effect of X-rays on a satellite from a nuclear burst. IEMP is internal radiation inside of a system, creating fields inside. And you may say, well, this is silly. Why do you need all these acronyms? Every one of these waveforms that are generated is different and takes a different type of protection. And here's the message. You got to know what you're talking about. Now, I understand the media and others like to call everything EMP, but if you use that term without some additional description, you don't know what you're talking about. As already discussed, a high-altitude burst, the thing about it that is so bad is it can create electromagnetic fields over a huge area. One or two bursts will cover a continental area. One burst can cover a continent, but a lot of those pictures are actually not relevant because there's no free lunch. The higher you go, the lower the radiation is when it gets down to the Earth's surface. So yes, you can illuminate the whole Earth, or the whole continent, North America, but the fields would be very low. So 2 bursts would be much worse than 1.
Well, how does this work compared to the lightning bolt?
It's far different. 2 orders of magnitude higher in frequency, fields typically higher. To get higher fields from a lightning attachment, you have to be so close that you're probably dead. Okay? But the frequency content's important too. Lightning is such low frequency that you can have shields built out of 10-foot by 10-foot metal rods with holes in between. The wavelength is hundreds of meters, so it doesn't penetrate. For EMP, it goes straight through. So you can't easily use lightning protection for EMP, and you'll see that's why we bring lightning in. Lightning protection does not work for EMP. It's absolutely useless.
And EMP doesn't occur in nature?
No. Closest thing is electrostatic discharge. Turns out that 10 centimeters from electrostatic discharge arc, when you touch something, you build up charge. It has a rise time of 700 picoseconds and a pulse width of 30 nanoseconds. That is the official international standard in which all electronics is tested to, and is one of the most difficult tests to survive. The thing is, though, that from that arc, the fields fall off rapidly. So when they do the testing on electronics, they have to touch with a gun about 20 places to make sure that they expose where people might touch. That's the problem. Okay, you've probably heard EMP bombs, EMP weapons, even geomagnetic storms. I do not like the idea of talking about a geomagnetic storm as an EMP. It's just confusing. Technically, almost any waveform that goes up and down, you could call a pulse, but it doesn't help. The mechanisms, everything is different. So there are formal definitions in the IEC and the IEEE, and we will use them here. High altitude EMP is a high altitude electromagnetic pulse from a nuclear detonation in space above 30 kilometers, 100,000 feet. It's the normal definition for space. The intentional electromagnetic interference is caused by the use of electromagnetic weapons by criminals and terrorists. This is also official definition in ERC and the IEC, IEMI. The reason for that is there is EMI, electromagnetic interference. It's very common in the field of those of us who also work to protect commercial electronics. We write the specs for PCs, for cell phones and so forth. That's the normal levels. But when the environment is so much higher, it's not financial. It doesn't make financial sense to try to protect everything against something that doesn't happen very often. But there are other ways to do the protection. So I'll go into some details. This will be probably the most technical chart I'm going to show. I'm not going to show any equations. I know it'll disappoint some of you. I know there are a few of you here that are really, really interested. But basically, this is a single waveform from a high altitude detonation. It's not precise. It has some variations with burst height and yield. But the first part, the first microsecond, and note, it goes from 10 to the minus 10th to about hundreds of seconds. There is no other transient like this that goes, even lightning. Lightning has several distinct processes that cover some of this time frame, but not in a single pulse. You look at the first pulse, reaches about 50,000 volts per meter. It's decreased by about a microsecond. A microsecond, we've developed some shorthand to help with the standards. We call this E1, early time HEMP. And so when you see E1 HEMP, it means the first microsecond. Why do we do this? Because these fields get into electronics in different ways because their frequency content is different. The higher frequencies penetrate through apertures and get on wires, short wires connected to equipment. The late time, the MHD, couples directly to the high voltage power grid and affects the transformers. Turns out the intermediate time, the E2, we haven't found much interest, many systems affected by it. When we put this together, we wanted to have the entire environment, but not all of it is important, it turns out. And it's shown on here, out of the nuclear device, the gamma rays coming from the device, which are produced by the neutrons through fission or fusion in the device, produce gamma rays in the device, which go outward. The neutrons come later and produce gamma rays in the Earth's atmosphere. And the gamma rays also scatter. So that's that intermediate time. The last is MHD, EMP, magnetohydrodynamic. This is the effect of essentially a high altitude bubble. Low energy particles in the atmosphere will move outwards, press against the Earth's magnetic field, cause the Earth's magnetic field to move. That movement is affected, is noticed at the Earth's surface, generates electric fields in the Earth. That's what the process is. And there's, probably on each of these, there's probably 30, 40, 50 documents, half of which or more are classified. Because especially the early time signal, if you can measure an early time signal from a high altitude burst, you know a lot about the nuclear design of the device. That's why it's sensitive. The others are not so important. On the other hand, almost nobody tests in the atmosphere anymore, which is a good thing. So if it's underground, there's nothing you can tell. One of the most interesting tests that the US did in 1962, July, was called the Starfish event. Everything about this test was publicized ahead of time. It's the only test we did that was done. I've never been able to trace down why that is. But it was a rocket launch from Johnston Island, which is about 1,400 kilometers southwest of Hawaii. It was a 1.4 megatons, 400 kilometers burst height. It was a scientific experiment. The whole purpose was not to see if the bomb would work. It was to look at the effects of the radiation on communications, the ionosphere. There were many HF ionosounds, thousands of miles apart, sending radio signals through the ionosphere, and they wanted to see what happened when the burst went off in the ionosphere. And of course, what happens is the ionosphere is blown away. The question is, how long does it take to come back? That was the nature of the experiment. It turns out we did have a few, actually one major EMP measurement. That's all. It was not an EMP test. There were some things that happened in Hawaii. Some street lights went out. Microwave outages occurred. There were nuisance effects. Alarms went off. And, in general, the feeling was, well, that's not so spectacular. Why do we care? Not a big deal. There was also a side effect that commercial satellites in 1962, there weren't a lot of satellites up then, were damaged. And they weren't damaged from the direct radiation, they were damaged by the charged particles that were injected in and formed a new radiation belt called the Starfish belt. That Starfish, and Van Allen was involved in this. And that Starfish belt only lasted 2 years because unlike the other radiation belts, they're not being fed by the sun. There's always we call it air chemistry. The particles eventually recombine and the radiation dissipates. But again, there was no effects on the ground. The picture on the right, that's the moon. But the light, it's 11 o'clock at night, it's an auroral display. That light was also seen about 4,000 miles away in New Zealand because the charged particles got into the Earth's magnetic field and were going along the magnetic field lines, bouncing back and forth. And this was announced ahead of time. People were on the hills over Honolulu taking pictures. It was on the cover of Life magazine, and within hours, the European newspaper edition of the Herald published all the details about the experiment. So it was announced. More interesting, that was 1962, the Russians also tested in 1962, October. They didn't test over the ocean, they tested over land, Kazakhstan. And in 1994, 32 years afterwards, they showed us and told us of all the problems they had with commercial systems, not military. And just like in the US, these are not experiments, these are things that just happened. One of the major things was several of their communication lines, including buried communication lines, were disrupted. And repeaters were damaged. Also, a power line had a disconnection of insulators where lines fell to the ground. Now, they say transmission line there, but that's a general term in engineering discipline. It was most likely a distribution line, not a high voltage transmission line. But that doesn't matter. It's a serious issue, and I'll talk about that later. The most spectacular thing about this is in 1962, they were so startled by what happened is they appointed a special committee to protect their country against EMP. And it was led by Khrushchev, Karaton, and Sakharov. Andre Sokol. But again, because they tested over land, they exposed a huge number of systems. Our closest was 1,400 kilometers away. That's a long distance. The EMP Commission asked us in 2003 to 2004 to take a look at the U.S. power grid potential vulnerabilities. We did this by looking at different aspects. We looked at distribution line insulators. We looked at high voltage substation electronic controls connected to external cables, power generation facility controls. Also, we were asked by the Congress, my company wrote contracts to Russian scientists. That was quite exciting. I never quite knew whether we were going to get anything for our money, but we did it, and they did. They were very, very good. This was in the early 2000s, high-level cooperation at that time. And they had some very, very good people, and they had more data than we did because they tested over land. And they identified, and correctly so, we agree with this, external system coupling is the major problem in E1 HEMP. That means that if you have a building with cables going out to collect information, whether it's telephone, power, or whatever, those become an antenna that collects the energy and brings it straight in. Now, you can deal with that by making sure that those signals are grounded before they enter the building. But typically in the power industry, almost all cables are brought inside the building and grounded inside, which means that all of the high energy comes inside the building, re-radiates, exposes all the equipment. Not a good thing. We also later, 2007, 2008, we did a full study of the E3, the late time HEMP, which is also very similar to the geomagnetic storm. And the reason, when I say similar, we actually look at the waveforms. Every geomagnetic storm creates a slightly different waveform, but they typically rise with a rise time of 10 to 100 seconds, okay? And pulse widths of hundreds of thousands of seconds. Okay, now it's a pulse, but it's often referred to as quasi-DC because it's so much lower frequency content than 50 or 60 hertz. So it looks like DC to the power network. But because it's a pulse, an electromagnetic pulse, it couples to the lines and creates a current flowing in the lines. And that starts all the trouble, and I'll get into that a little later. And there's a very high risk of voltage collapse. We studied the 1989 Hydro-Quebec failure to a geomagnetic storm. We compared the waveforms, and then we said, well, gee, they're very similar, and now here's a storm that happens in Quebec, and it takes down the entire high voltage network. Was down for 9 hours, and it collapsed in 93 seconds from beginning of the storm to the end. So it's very, very fast. So we also took a look at the risk to the transformers. It's not the wires we're worried about, it's the things at the end. And we handed our data off to analysts for the EMP Commission, and the EMP Commission financial analysts looked at how long it takes to replace transformers, the cost, and the cost to society without having power. And a lot of the estimates were the possibility of a year without power. And not everywhere, certainly some areas would be able to recover, but not the whole grid. And we looked at hardening techniques and costs. Costs are very important. In terms of E1 HEMP, I'm going to jump back and forth a little bit. One of the issues we have in the U.S. here, you're not in as bad a shape in Texas because you have a separate power grid with a lower number of companies that have to be controlling the grid. But the three grids that we have in the U.S., Eastern, Western, and Texas, there are about 150 major companies controlling the grid, keeping it balanced. In 2003 power outage in Ohio, 4 power companies were not successful in working between themselves to keep the grid alive, and that one affected 100 million people. They worked for 4 hours trying to stabilize the grid, and when it got out of reach, one wire hit a tree, 1 second was all it took for a complete collapse of the Northeast, including Canada. So there is an issue with having so many companies involved in controlling the grid. It's not an easy job. But it means also that there are a lot of control centers, there are a lot of power plants, And there are a lot of things that can happen. And here's one of the issues. A high-altitude burst is 170 kilometers over Ohio. Why Ohio? Turns out that the eastern grid is much more important in terms of numbers of transformers, amount of population, amount of GDP, and all of these factors. I'm not saying Texas isn't important, please. but I'm just saying, and this was the EMP Commission selected this. And again, it's not the burst over Omaha or Kansas, which, by the way, was a drawing that I made in 1968 when I was in the Air Force, and everybody's been using it since. I kind of regret it. But here's what happens. These are the substations that are exposed. I'm not saying they're damaged, but they're all exposed by that one burst. And here's the thing. The exposure, the arrival of the disturbances, if there is one, is within one power cycle. It's about 10 milliseconds. The reason it's not instantaneous is it's a spherical wave coming from space, and the Earth is spherical in the other direction, so there's a little bit of extra time. But it's far different than any disturbance on the ground, which has to propagate at the speed of light outward. So you have a lot more delays involved. Okay, why do we care about substations? They have a huge number of cables that go from a control house out to the high voltage network in the substation. Here's just an example. They call them a trenway. Inside is a lot of cables. This is not a shielded geometry. You notice the crushed gravel around it. It's very low conductivity gravel, which means electromagnetic, and concrete is very easy for electromagnetic fields to penetrate. In this case, they've got metal on top, although it's not very well seated. There are a lot of places where concrete or wood is used. The point is these are easily exposed. Then they come inside, typically, and are grounded inside. The green wires are the ground wires. Well, in EMP, ground wires are antennas. They radiate. But worse than that, at high frequencies, at 1 megahertz and below for lightning, these might be an ohm, which is a decent ground. And then, of course, it is further grounded into the ground grid of the substation. However, when you're at 100 megahertz, it now has an impedance, a reactive part, that runs it up into the hundreds of thousands of ohms, which means that none of the current that's on those other cables coming in is going to go on the ground wires, just going to continue on the signal wires to the equipment directly. And this is an older substation where everything's above. A lot of the newer ones, they use computer type 4s below. But the other problem is, even though these are nice metal cabinets, they're not shielded cabinets, they're just metal cabinets, which is better than an open cabinet for sure. But the cables just run directly in. There's no grounding of the cables before they go into these racks. And the reason that is you'd have to peel off the insulation on every one. You'd have to have a connector. It takes a lot of work to do that. So it's not a good design. People who build, say for the military, special secure racks, every single cable going in and out is got a shielded connector. And the idea is that under that black insulation, there's a metal shield. That's an antenna. There's current running on it. If you ground that at the metal rack, then that current flows on the outside. If you just let the insulator run through, current stays on and runs all the way in. And that's a very, very bad design. Now, there's no standard that says how they should do that. And that's why we're working so hard on standards about how to do this protection. The other thing we did is we looked at all the different ways that energy can get in. And by the way, we did not do everything on a worst case basis. You don't want to do that. You don't want to take the worst field and the worst geometry and come up. We did things statistically because we wanted to have a distribution. Worst case is fine for the military. It's not clear that it's the right approach for commercial, with the exception of some very, very critical facility. So we looked at all the ways energy could get in. Then we took a look at the equipment and we tested all the equipment inside to failure, because there is no magic spec that says this computer should survive 50,000 volts per meter and 20 kilovolts of a voltage pulse coming in on every cable into USB, into Thunderbolt, into all of these things. We actually tested all this equipment, relays, programmable logic controls, computers, remote terminal units, to failure on every port, and that's difficult. You have to test at low levels and go around every port, then go up one level again, and then things start to go bad. Sometimes when things go bad, they affect other ports, because there's many places cables can connect to a lot of these boxes. And we found that upset and damage begins in the 1 to 2 kilovolt range for conducted transients. This is the field getting into cables and going into the computers. And so we combined real nuclear bursts, putting real currents on cables for different types of substations, and then looked at what currents were getting inside and what were the levels that the equipment could withstand, and then came up with probability of failure for hundreds or thousands of substations for the whole country, everyone exposed. We can do that. Now, of course, it's probabilistic, and we're attempting to not bias it, but there's no guarantee it'll be precise. But and not every power company buys exactly the same relay, although there are only a few major companies that make them. We also got input from the Soviet or Russian scientists, excuse me. They provided the EMP Commission, through us, a review of the HEMP effects on systems, commercial systems, from their nuclear atmospheric tests and simulators. And by the way, we did a huge amount of testing in simulators. We measured the fields from the nuclear bursts in 1962. We built models to try to understand if the burst had been higher or lower, or different yields, how the field would change. Then we looked at what is the maximum field we think occurs. We built simulators and large antenna structures with pulsars to make those fields. And then we tested airplanes, missiles, Minuteman, MX, B-52, airborne command posts. These were all tested to these big fields. And what we found is over the years, more and more electronics, modern electronics in these systems, the more failures there were. So that is the explanation of why Honolulu didn't completely stop in 1962. But rather, when you test newer and newer equipment, it's extremely vulnerable. It's not designed for this, and digital electronics is much more vulnerable. The Russians came up with a really great idea that I tried for years to get somebody to build one, even to pay Russia to deliver one for us. It is a portable EMP simulator for lines. It would be absolutely wonderful for the power system. Say, this is the case where they had a power generating truck and a vehicle that needed power. And this is the simulator. And it would send a current down a wire, and the wire would be parallel to the wire they wanted to test. It's just inductive coupling. You get a current, creates a magnetic field, but the nice thing about this is it's traveling at near the speed of light with some effect with the ground. And that's just like the EMP wave coming across. And so you don't have to break into the cube. The way the U.S. does typically testing is to break open the cable, find all the wires, and drive different wires in different combinations. The problem with that is you can't do normal operation. You're just seeing if something will happen. Well, what the Russians found out is that if they were operating this power system when they did this test, they had failure. If they were not operating, nothing happens, no problem. Power on testing is critical. What happened is the current that was induced was high enough that there was a surge arrestor. The surge arrestor fired, but the power that was being carried on the power line carried through that arc and damaged the system. In fact, they told us that it created a fire.
So what sort of device or equipment have you used to generate that?
Oh, yeah. Well, typically these are capacitor banks similar to the HEMP system. You have capacitors that you charge up slowly to get to the high level, you discharge them rapidly, and you can generate with some pulse forming networks. You can shape the pulses. And that's one of the problems for intentional EMI. The same technology that allows solid-state devices in our computers to be very small, they've also done the same thing with high voltage equipment, IGBTs and so forth, which now you can generate very big pulses in more compact areas. Probably do something smaller than this. We built several of these trucks. We're testing the MX Peacekeeper in the rail mode version. We actually induced currents, huge currents on the rails underneath the train.
Stand a little bit closer to the microphone.
I'm sorry, excuse me, that's right, for the tape. That was, unfortunately, as Bob can tell you, the days of MX, I think we looked at 35 basing modes, some of them for only a couple of weeks, and then in the end, they put the missile into a silo just like we did before. But we had to do the studies. Anyway, this is very intriguing. The idea with this is you could go to a power substation and lay this cable down right over the trench. Now, with one characteristic, I would argue we'd want to dial on it to start very low. The idea would not be to show that you can damage something. That's not really an honest test. We could do that, but nobody's going to be happy with that. What you want to show is there a vulnerability at what level? And then you can do your protection, or better yet, protect it, then test it. But don't just go out and do it. But this would be very easy. We're talking about minutes to lay this out and do one test and go on to the next cable, I'm going to try, the EMP Commission is going to be meeting again probably in a few weeks, and I'll try again to convince them to go for this. We'll see. And the Russians are probably still interested in building one for us. Not that it's that hard, it's just that they've done it already. This is another issue, insulator destruction. This is the same power on issue. The Russians did this testing for the EMP Commission where they tested distribution insulators. These are at the 10 kV power level, so it's medium voltage. It's the wires in your neighborhood that bring power to your home. And what they found is that if they tested the insulator with transients due to EMP or lightning, nothing really happened. And the arc would go across, but the insulator would be fine. If they powered it, the insulator, we're talking about 2,000 amps of power at 60 hertz. In some cases, about 10% of the cases destroyed the insulator. Now, if you remember that picture I showed you some time ago, right here. Puncture, temporary disconnection of transmission. The temporary is that after they got out there and repaired the line, then they raised it back up again. The insulator was damaged. The insulators hold the wire there. If they are physically damaged, the wire goes to ground, and then, of course, the circuit is dead. So they knew about this. And in fact, the research they did for us, I'm sure, was probably recycled, but we didn't care. They wrote very, very nice reports. We actually I inspected their test setups. And they wrote several IEEE and conference papers that were very, very technical and excellent. And that's one of the things we always look for, technical accuracy, because anybody can say they can do something, but until they've actually done an experiment and written it up and shown the results, it's very easy to fake such things. So the conclusions of the EMP Commission is one or a few high altitude bursts can produce E1 HEMP simultaneously over a wide area within one power cycle. E3, which I haven't talked about in a lot of detail, I'll talk about more with geomagnetic storms, is likely to cause voltage collapse of the power grid with some possibility of damage to large transformers. And the damage is more likely to occur if the voltage collapse is slow. If the voltage collapse is fast, or if somebody turns off the power system, it's this voltage pulse that induces a current that sets the whole problem in motion. It's the DC, quasi-DC current plus the AC current. If you just have the DC current, it's no problem. So, and as you know, power is critical because it affects so many of the other infrastructures, and that was one of the major conclusions of the EMP Commission. I'll go much faster here. Intentional EMI is the use of local electromagnetic weapons, and this is in the frequency domain. It's a qualitative chart, but it shows the E1 HEMP in the frequency domain starting to decrease around 10 megahertz and decreasing sharply after 300. Lightning tends to decrease sharply after 1 megahertz. The most of the energy is at lower frequencies, and this has to do with electromagnetic characteristics of how they interact and create currents. At the higher frequencies is where we see both wideband and narrowband threats. They have sometimes different names. We like, from a scientific point of view, to talk about wideband and narrowband, not HPM, HERF, or ultra-wideband. I only put them there because people are more used to that terminology, but now ultra-wideband is a useless term because there's communications at ultra-wideband, and the FCC has defined ultra-wideband as 500 megahertz bandwidth. Well, what we're talking about here is a pulse versus a CW signal. That's what we're talking about. And those are two ways of generating these signals that have been demonstrated, built, and made, and are sold. And they both have different types of effects on electronics. IMI is defined by the IEC and was started off at a particular conference. Notice it's the malicious generation of energy for noise or signals, but it's not only damage, it's disrupting, confusing, and damaging. And at first this was called electromagnetic terrorism, but we decided that that wasn't appropriate. Terrorists can use it and have used it. In fact, the biggest users of electromagnetic weapons in actual wartime was in southern Russia. I've just forgotten the name of the group that was doing it, but they actually used weapons against the Russian military. Chechnya. And there have been many attacks from a criminal point of view. The favorite one is to take out video cameras from a distance with an electromagnetic weapon, and it's very easy to do. We've actually published papers to show that it's possible. One thing we don't do is we don't try to tell people how to build the weapons, although they seem to know how to do that themselves. IMI is not new. It really started out in 1999. The IEC was involved, the IEEE is involved, EMC conferences are involved. We're talking about an electromagnetic weapon has an energy source, typically a battery, capacitors, and an antenna. Now, there are many ways people can go. You can have a highly efficient antenna, which directs the energy a very far distance, but it might be big. Or you can have a very small antenna that spills the energy in all directions, which means then you have to have a stronger source. They've mainly been designed by the military, but in the military it doesn't work so well. Even the CHAMP system. CHAMP system is not designed against military targets. It's defined against the infrastructures to try to put power systems out, without damaging a city, to try to take the electronics out so that it could be rebuilt later. And the other problem with military to military is it's very easy to protect by shielding, and that's done. So it's sort of a battle between building a bigger weapon and a bigger shield. And whereas on the commercial side, nobody's protecting this equipment. Okay, that's the important part. It doesn't mean it can't be protected. Here's an article I wrote, and I apologize for the title. The IEEE spectrum is different than IEEE journals. And I almost had to quit writing the paper because they were so crazy with how they wanted to label every picture and so forth. But they did go for that title. You can see that they were so intrigued with what they had done, they had built that model of an electromagnetic weapon, and they actually wrote an article the next month on how they built it. And they thought that was so cool. It's not real, but it's a mock-up of this, and this is real. This was built by the Germans, Deal munition system. It is a very powerful weapon. It can be used outside a building or inside of the, if they get it inside of the building, there's nothing inside that's going to work afterwards. And it has a 3-hour capability if it's not discovered. The one we have a smaller one, not as powerful as this, in our laboratory. We test equipment. Ours runs for 3 days on a truck battery. Now you say, why is that? Energy and power are different. Peak power can get to tens of thousands of volts per meter times the magnetic field, EH. But these pulses, the one we have in our lab, produces a pulse width of 100 picoseconds and a rise time of 50 picoseconds. And it's manufactured by a company in the UK, costs about $10,000. And we've been using it for several years now. And there's no commercial equipment that can withstand the fields from this thing. So, yes, sir.
There's a company in Austin called, I believe it's AELC, that also makes those kind of.
Yeah, they started very late. We knew about this long before they did, but it's fine. Anybody can build them. It's not hard. I mean, the thing to do is to get the cost down. But you see, the people, I know the people who built this at Deal, what they did is they figured out which waveforms were the most dangerous for equipment through very careful testing of electronics, the things that they wanted to target. And by the way, this is designed for their special operations troops. Before they go into criminal or terrorist locations, and they're outside the door, they turn it on, shut down all the computers so that they can't remove some of the data, take it away. The computers are essentially shut down. That's what they use it for. And that's why it's relatively light, 62 pounds. I guess the German guys are pretty strong. I'm not sure I can handle that. But like I said, anybody can go build. And there are a lot of people who make pulses that are absolutely useless. They're very powerful. One of the key things is if they tell you the field level and don't give you a lot of details about the waveform, the wave shape and the frequency domain. Those of us who have been doing research, there's hundreds of papers on testing equipment. And we know, in fact, a colleague of mine, Carl Baum, said the right way to design this stuff is you figure out exactly what your target is, what you want to affect, and then you build the antenna and the source to match that. Yes?
So is this an antenna that you take out of the box and unroll?
No, it does it inside with the thing closed. It's a plastic case.
Right. Oh, okay.
It's a plastic case, sorry. Yeah, a strong plastic case, I would imagine.
So that's
Yeah.
a coil.
And that's what I was saying before. It's a very simple antenna. It's not very effective. It's omnidirectional.
Basically a coil oscillator.
Right. Yeah, exactly. And what you want, if you wanted to make this thing more effective, in fact, they have a version of it. All they do is they put up a corner reflector behind it. It's also compact. They open it up, and it actually boosts it a factor of 4, up to 500 kV. This is the most powerful one ever built at the Air Force Weapons Lab, now AFRL. It's called the JOLT. It's fully published. I have no idea why they published it. So much for security, I guess. It's the most powerful published weapon ever built. It produces 53,000 volts per meter at 100 meters range. 100 meters. It produces 5,000 volts per meter at a kilometer, and most commercial electronics fails between 2 and 5. Okay. It was designed by Carl Baum. Here's the basic geometry, if you wish. You're outside a building, you got a parking lot, truck with fiberglass sides, you can put whatever. Well, and there's been lots, you go on the web, the Navy and others have built up all sorts of different devices. Even if you can buy a surplus radar, small radar, it works great. Anything in the gigahertz range is going to wreak havoc with electronics. Now, it shows the fields coupling and creating currents and voltages to the telephone and the power lines outside. Now, of course, if they're buried, it doesn't work as well. The high frequencies don't penetrate the ground very well. It shows signals going through a window, but actually that's not necessary. A lot of buildings have very poor shielding. Typical concrete building can be quite bad. You need metal buildings to really have any shielding. What's shown there is once the signals get on the wiring, we find certainly the fields go into the equipment, but the first failures at the lowest levels are from the fields getting to the wires and the currents and voltages running inside, because they run directly inside. They have some protection, but not against these threats. So the type of things that IMI can do, it's the same, similar frequency band, but higher than E1 HEMP. It'll have the same types of impact, substation control electronics, control centers, power generation controls, inverters, including distributed generators, solar and wind. All these solar and wind generators are converting either an AC wind to another AC to a DC to back to the AC. There's a lot of converters involved. These converters are full of electronics. They're not simple anymore. Almost all the inverters are very high efficiency. They have electronics. We've been testing them. And they don't tolerate very high levels very well. So this is an issue. Doesn't mean you can't fix them. You can. And that's what we're working on, making standards that if you want to do it, they're not going to be mandatory. If you want to protect against these threats, here's what you do. The reason they're not going to be mandatory is we can't test everything and make everything survive these types of threats. It should be up to the customer to decide what's important and what is his job. But what does he have to do? Does he have to keep operating? Can he be down for a few minutes? Can he be down for a few hours? You know, what are the criteria? And that's the same in the military. The military has special definitions for hardening that have to do with the level of importance. If you're a military supply office, not so critical. If you're trying to get a message to the president, pretty critical. So there's a lot of differences. There's one difference about IMI and HEMP. Physical security can help because distance is important for the electromagnetic. It is not for the electromagnetic weapon. It's not important for the high altitude burst because that field is not changing once it reaches the ground. Most people misunderstand this. Even though the radiation comes from the device, the gamma ray radiation, the electromagnetic field, say the burst at 400 kilometers, the electromagnetic field is generated down at 50 kilometers in the atmosphere. So it's generated a long distance away from the source point. And that gives it an effective radiating antenna, which is huge, hundreds of kilometers long. So the field walls off very slowly. Whereas if you have a fixed device, like that deal device, based on the size, it's falling off roughly a factor of 2 each doubling of size, distance. Okay, just to mention, several U.S. power companies are combining E1 HEMP and IMI hardening measures for control centers. They're doing both together. The European Union just finished 3 projects. They spent 15 million euros dealing with the impacts of IMI on the critical infrastructure. And one of their biggest efforts was on high-speed rail. They're worried about high-speed rail. IMI detectors are being built by several companies. It's been going slow. We'd really like to see more of them out there because these things can last for hours. And if you're having problems, it'd be nice to know if you're under attack. And the only way you can do that is with some sort of measurement. You need a detector. There are a lot of papers looking at IMI. There's even a new one where they've tested radiation detectors, you know, for, say there's been a radiological event. If you illuminate the detectors, they can read incorrectly. They can read either high or low by orders of magnitude. And so you can imagine first responders coming out, the radiation detectors looking for radiation all at once, their meters are pinned, they got to leave. And they can't deal with the threat, even though there is no threat. And some interesting things. There's been a new discovery in Sweden where some 3-layer energy-efficient glass can produce up to 60 dB. That's 3 orders of magnitude attenuation of electromagnetic fields between 1 and 10 gigahertz. It has to do with a thin film of silver that's put into some of the triple pane glass. So this would be fantastic if we could really be sure and test it all, and this is based on test. And video cameras, I already mentioned, very bad. In fact, I call it the, I'm trying to remember the name of the Mission Impossible, I guess it was, MI, where they used to put up a picture in front of the cameras. Well, in our test lab, when we tested the cameras, they froze frame with nobody there. And it stayed that way, no signal, no information that it was frozen. You had to turn it off and turn it on. So if you're looking at an empty hallway, it stayed empty. Okay, geomagnetic storms, last part. We had the big blackout in Quebec. There have been a lot of power companies over the years. Since then, 1989 was a wake-up call. I mean, Bob was absolutely right when he mentioned that this, big storms have occurred and have been noticed back to 1859 with the Carrington event. But this was a wake-up call because it's with the modern power grids, and people were quite surprised. After that, many of these countries, including the U.S., had their local grids modeled and tested against past storms to see if we could predict the current flow in every wire and places where there were measurements, compare the calculations to measurements. And that model is very successful. There are tens of papers published on that that you can find in various journals. One unhappy thing, though, is the higher the voltage of the grid, the more vulnerable it is to geomagnetic storms. And this has to do with the fact that newer, higher voltage grids were built later and therefore used a new technology, lower resistance wiring, basically. They used the best wiring they could find, whereas the old wiring was high resistance. And it's a voltage source between the two transformers at each end. The lower the resistance, the higher the current. It's very simple. It turns out that, as I said before, geomagnetic storms and E3 HEMP are very close to the same. The estimated level of the field that took down Quebec was about 1 to 2 volts per kilometer, okay, or millivolts per meter, if you wish. The E3 HEMP standard for the IEC is 40. That's about 20 times higher than what Quebec saw. And the results from modeling are very reliable. It's a very simple modeling problem. It's resistance only, no capacitance, no inductance. Let me go through this. I'm running over here. This is a coronal mass ejection from the sun that starts the whole process. This is not a flare. There is some confusion about that. Flares only tell you that a sunspot region is active. The flare itself sends X-ray radiation to the Earth and gets here in about 7 or 8 minutes. The coronal mass ejection is charged particles that flow toward the Earth, take about 2 days to get here, much lower energy. It turns out that coronal mass ejections often follow flares, but not always. So you can't just look at a flare and say there's going to be a coronal mass ejection. This is a chart put together by a colleague of mine, John Kappenman. The blue lines are the sunspot cycles, just the number of sunspots, and it's highly average. It's not even a day-to-day variations are not shown. If I showed the day-to-day variations from the past, you wouldn't even be able to see the chart. Sometimes you can have a situation where you'll have maybe 50% increase over a couple of days, and then they go away. But some sunspots last a long time. But the main point is the blue is at the sun, the red is big storms noticed here at Earth. And you can see that in the 60s, there was some correlation near the peak and after, but you can take a look at 1985, 86, solar minimum. It only takes one active sunspot to create a coronal mass ejection. And there's no physics that tells us that you need to have more sunspots to have a big storm from one sunspot. And in fact, I think in the Carrington event, it was also near solar minimum when the storm occurred. This is just a little bit of the physics. What I'm showing in the upper right is some modeling we put together. We were the first to do it, where we took all sorts of magnetometer locations from observatories. They're all time histories that they measure. We took their locations and put them together, and why did it? Okay, there we go. We put them together into contours as a function of time. So at the same time, we're looking at the magnetic fields. This is on the Earth, but it represents the charged particles flowing in the ionosphere. And this is a 4 sequence. It's only 1 minute time in between because that's all we had at the time. And this is data. It's not a calculation. This is interpolating among about 30 observatories. First one, upper left, normal situation. There's always solar wind, and there's always charged particles coming down along the magnetic field lines and forming an oval around the magnetic North Pole and also South Pole. And that's just current that's flowing. What happens is when a high increase in charged particles hits the Earth and gets into that system, then it moves further south. The one on the upper right, 244, in the Montreal area, it's not actually at the maximum yet. It's maximum here, 1 minute later, over Winnipeg, but by this time, Hydro-Quebec had already collapsed. Oh, I'm sorry. Hydro-Quebec had already collapsed at that time. Okay, so that's all it took. Now, since then, we've known and we've argued they ought to have better than 1 minute data, and almost everybody. We started 1 second data back in the early 90s for ourselves. We ran our magnetometer. It's very easy to do. And now most of the observatories are going down to 1 second. And that's because it actually matters. If you take a time waveform of magnetic field, 1 minute spacing, calculate the electric fields, then you do the same time waveform with 1 second space, typically the electric fields are 2 to 3 times higher because it's the derivative of the magnetic field that creates the electric field. And if you can't resolve the derivative, you don't get the field. This is the damage that occurred to one transformer in the United States at the time of the Hydro-Quebec failure. It was in New Jersey, nuclear power plant. Interesting that the fields were worse over Montreal, but here's one transformer that failed that was in the U.S. It's thought to be that it was an older transformer, maybe it was near end of life, but it's not really known. A lot of work is going on now in Seagray. The High Voltage International Group is looking at transformer damage from DC currents to see what are the mechanisms and how does it happen. This is the model that we have for the whole U.S. You notice in the West there are a lot of gaps. That's because there are series capacitors on many of the lines so that there's no way for DC current to pass. We only model those where the current can pass. But the other interesting thing is the voltages for the U.S. 500 and 765 kV serve 86% of the U.S. population. Sure, there's a lot of 345 and 230 out there, but most of the population is served by the higher voltages. The reason that's significant is the higher voltages are more sensitive. The other reason for the higher voltages are longer lines too. If you're in an area you don't need longer lines, then there's no need to go there. Here's just a really quick look. Again, what we've done is we model old storms to see what the grid will collect, and then we compare it to where there are measurements. Unfortunately, there are very few measurements. We're talking about in the time of the 80s and 90s, maybe 20 for the whole U.S. In our opinion, every transformer should have a monitor on it. It's not expensive. It costs maybe $5,000 and very easy. We've done it ourselves at transformers where we had cooperation. But here's a case at one instant over the northeastern U.S. And this was not a particularly big storm. This is not a huge storm. Then we looked at 5 substations where they had GIC measurements, and then we calculated, and not just the peak, this is just the peak, but we do very well with the entire waveform. And you know, there's currents up to 70 amps. It's not a huge number. You start to get worried if the total neutron current gets into the 200 to 300 amps. We have calculated for a Carrington level storm, there would be 500 transformers with more than 300 amps falling in, which means they're at risk of damage. And for the EMP Commission, we calculated where blackouts were likely to occur if we had a Carrington type of storm. It's very conservative. It does not assume any cascading of the effects, which is likely to occur. Last, before I get off the stage here, very recent geomagnetic storm development called an executive order from President Obama titled Coordinating Efforts to Prepare the Nation for Space Weather Events. Notice the date, 13 October. And it's a direction to all government departments to take action. And I just highlighted, well, first, they talk about solar flares, energetic particles, geomagnetic disturbances, talk about GPS, satellite operations, communication, aviation, and the electric grid. And then it says, extreme space weather events, those that could significantly degrade the critical infrastructure, could disable large portions of the electric power grid, resulting in cascading failures that would affect key services such as water supply, healthcare, and transportation. And just one of the actions, I just noted there are many, it's about a 5-page executive order. Within 120 days, the Secretary of Energy, along with the Secretary of Homeland Security, shall develop a plan to test and evaluate devices that will mitigate the effects of geomagnetic disturbances on the electric power grid. This is quite interesting, especially since NERC just finished a study which said no hardening is necessary, just take operational, try to be careful, do certain policies, and there are some things you can do legitimately for the voltage collapse. But this was quite a surprise. Didn't know it was coming. The EMP Commission is quite interested in it because, again, the E3 hemp is much, much worse than a geomagnetic storm. So apparently, and it also says to consult with the chairman of FERC, not to ask FERC what to do, but to consult. And I had forgotten, I had at the back, the protection. We've been protecting against electromagnetic threats for years. Radar, radio stations, MRI machines cause a lot of problems. They have to be shielded from the rest of the hospital. Cellular phones are bad actors. There's a large number of automobile issues where cars have accelerated due to cell phones, et cetera, et cetera. These things have happened. But here's the key. When something like this happens, we figure out how did it happen, and then we fix it. With the things I'm talking about, we don't have much opportunity, and we do have the Quebec situation. Well, at least we can look at that. But often, unless you do something ahead of time to protect, once it happens, it can be so bad, it's too late. We're not going to learn from it. It's going to be too late. And we have in standards assessment steps where you go through for existing buildings and look at different ways to evaluate how good the building is. We actually have measured over 100 buildings, power system buildings, to their shielding effectiveness. The highest we've ever measured is 29 dB, which is about a factor, it's actually 30 dB. 20 dB is a factor of 10 reduction. But there's an awful lot. Concrete without rebar, brick, it's about 5. It's very, very low. We know how to do protection. Here are some of the protection schematics and various standards. General protection, you can improve a building by adding external shielding, internal shielding, shielded rooms or racks, but the best is a new metallic building. You can do that when you're building the new one, say. External grounding for external cables, that is a major, major issue. If that's not done, you're defeating everything. You can work on the internal cabling, you can put in filters, surge arresters. There's many possibilities. The standards go through options. They don't want to force one way to do everything. It depends on your situation. The IEC has been writing standards. 22 we have written. I've been chairman of this group recently, just stepped down, but we've written 22 standards. They deal with very small pieces of the problem. The most important one, though, is a new one, which I am the project leader, the application guide, and that's a document that tells you how to harden buildings, dealing with all these other standards, pulling what we need out of each one. And that document has just gone in for a committee draft for vote last week and will be published sometime next year. And so also the ITUT has come up with protection guides for high altitude EMP and high power electromagnetics. Seagray has done work on protecting substations, and the IEEE. So a lot of effort is going on internationally. Okay, thank you. Yes, sorry.
Question?
Well, probably just one because I did go over. Sorry.
If I were worked for a company that had critical infrastructure like a refinery or chem plant or a pipeline or something like, or a hospital that served the public, and I wanted to persuade my management to do something effective to get ready for some of these threats, what should I do? And before you answer that question, I want to do one announcement. I have created a group on the Facebook called Protect the Texas Grid. I would welcome anybody to join that. I actually found out about this meeting because one of our 700 members posted about the meeting here. We welcome you there because we're working with Senator Hall on the legislation. But what do we need to do?
I think probably the best place is to look at the IEC standards. It's the best collection of standards for protecting commercial equipment against both intentional EMI and EMP. There's nothing close to it. And I know that because I helped write the mill standards.